This is the topic 2 honors on symmetry and even and odd functions. So these notes up here, so if we look at these first notes, graphs can have many kinds of symmetry. We're going to look at symmetry over the y-axis, x-axis, and the origin. So looking at the graph y equals x squared, the graph has symmetry over the y-axis, meaning like if you take this piece of the graph and flip it over the y, you get that piece of the graph. So that's why it has y symmetry. But in other words, if you have the point, so like on this graph, we would have the point 2, 4. And if it's symmetrical, then we also have the point -2, 4. So negative of the x, but the y stays the same. For the graph x equals y squared, this graph has symmetry over the x-axis. So it has the point like 4, 2. And in this case, our x stays the same, but our y is now the negative. Then for origin symmetry. So origin symmetry is when you have the point xy, so and let's say 1, 1. And then you would then have the point -1, -1. So both x and y now become negative, the opposite sign. So to test an equation if it has symmetry, so based off of looking at the graph, you can look, so for the x, like we went over the y-axis, it flips over the y-axis. The x-axis, go across the x-axis. And then something about origin is it flips over the y-axis, and then you flip it over the x-axis. Another way to look at origin is if you flip this upside down, it would look the same. So turn your paper upside down, and the graph still looks like x equals y squared. This is the wrong equation. This should be y equals x cubed. Okay. But for an equation, since you can't look at the graph and tell if it has symmetry, we have different ways of finding each symmetry. So for y-axis, we're going to put a negative x in for every x in the equation, and if it matches the original, then it has y-axis. For x-axis, we're going to put a negative y in for the y, and if it matches the original, it has x-axis symmetry. And then origin, you put in negative x and negative y, and it should equal the original to have origin symmetry. So let's do a couple examples and state if there is symmetry or none. So let's start with y-axis by plugging in negative x, y squared plus 2, and this is for y-axis. So it would be negative x equals y squared plus 2. I could divide everything by -1 and get x equals negative y squared minus 2. That does not equal the original, so this does not have y-axis symmetry. Next, we can check for x-axis. And we're going to put in a negative y. So x equals negative y squared plus 2, which x equals a negative squared becomes positive, and that does equal the original, so this has x-axis symmetry. And if you have one, then you don't have the others, so this has x-axis symmetry. All right, moving on to the next one. Again, let's start with y-axis and plug in negative x's. So y equals negative x to the 4th minus negative x squared. So don't forget to plug in a negative x for every x in the equation. So a negative to the 4th power becomes positive, and a negative to the 2nd power becomes positive. But don't forget about that minus that was still there. And that does equal the original, so this has y-axis symmetry. Symmetry. We can just go ahead and use this one to test for origin. So if we plug in a negative y and that negative x, you would see that we get y equals negative x to the fourth plus x squared, which doesn't equal the original, and that's why this one's not origin. I just wanted us to practice origin before this last one. So y equals x cubed plus x. So let's test out y-axis to start. So y equals negative x cubed plus negative x, which is a negative to the third power stays negative, and a positive times a negative is a negative. That doesn't equal the original, so not y-axis. So let's test x-axis, plugging in a negative y. So I'm going to divide everything by negative 1. And that does not equal the original, so this doesn't have x-axis. So let's test for origin. And we're replacing negative x and negative y. So negative y equals negative x cubed minus x. And I'm going to divide everything by negative 1. And that does equal the original, so this has origin symmetry. Moving on to even and odd functions. Even functions are symmetric over the y-axis, and odd functions are symmetric over the origin. So you can test for even and odd by, if you're given the graph, to look to see if it has y-axis symmetry, we would know it would be an odd function. If it has origin symmetry, then we know it is odd, and then the even was the y-axis, sorry. But if we do not have the graph given to us, and we just have the equation, to solve for it, we're going to plug in negative x, and if it matches the original, then it has even symmetry. And then we're going to test for odd by putting a negative in front of our function, and it should get what we got in even, not the original. So let's look at these examples. So we always want to test for even first by plugging in a negative for every x in the function. So negative x minus 2 would be negative x minus 2. We're going to see if that matches the original, and it doesn't. So this is not an even function. And now we move to odd. For the odd function, we put a negative and then parentheses and then the function. Distribute our negative and see if it matches what we ended up with in even. This does not match what we got in even, so this is neither even or odd. Alright, x to the fifth minus x. Again, start by testing for even by putting in a negative x for every x in the function. And that would be negative x to the fifth plus x. That does not match the original, so this is not even. Now we're going to test for odd by putting a negative in front of the function. And we would get negative x to the fifth by distributing our negative plus x. That does match what we got in even. So this is an odd function. And last example, again, test for even by plugging in negative x for every x. That would be x to the fourth plus 3. That does match what our original equation was, so this is an even function. And that's all for this video.